Out of the more than 200 moons orbiting the planets in our solar system, only a handful truly matter to science. Most are dead, frozen rocks. A few are interesting. But one of them, sitting almost 3 billion miles from the Sun, hidden behind Neptune, might be the single most important moon ever discovered. And almost no one talks about it. Its name is Triton, and the more scientists study it, the more they realize this one distant world holds answers to questions astronomers have been chasing for over a century. How do solar systems actually form? Where does life become possible? What happens to a moon that doesn't belong where we found it? Triton answers all of them at the same time. It orbits its planet backwards. It erupts frozen nitrogen miles into the sky. It may hide an ocean of liquid water beneath its icy shell. It came from somewhere it was never meant to be, and it's slowly being pulled toward its own destruction. Today we're going to talk about why a moon most people have never even heard of might be one of the most important worlds in the entire solar system. To understand why this almost forgotten moon means so much to modern science, you have to go back almost 200 years to a quiet evening in October of 1846. Just 17 days earlier, astronomers had finally confirmed the existence of Neptune itself, the eighth planet, found not by accident but through pure mathematics. People were still arguing over who deserved credit for the discovery when a British amateur astronomer named William Lassell pointed his own private telescope toward this new world and noticed something faint moving beside it. A small dot of light holding its position night after night, refusing to drift away. He had just discovered Triton, and although neither he nor anyone else realized it at the time, he had stumbled onto a moon that would slowly, over the next century and a half, rewrite parts of how we understand our solar system. What's strange is how quietly Triton has lived in our textbooks ever since. We've known about it for almost as long as we've known about Neptune. And yet, even today, most people couldn't tell you a single thing about it. It hides in the shadow of its planet the same way Neptune hides in the shadow of Jupiter and Saturn. Most of us grow up hearing about Saturn's rings, Jupiter's red storm, Mars and its rovers. But Triton, sitting almost 3 billion miles from the Sun, almost 3 times farther from us than Saturn, almost never makes it into the conversation. It's the kind of place that feels too far, too cold, and too obscure to matter. And that turns out to be one of the great misunderstandings in modern astronomy. To picture where Triton actually lives, you have to imagine traveling outward from the Sun and watching the light slowly fade. By the time you reach Neptune, sunlight is roughly 900 times weaker than what we feel here on Earth. The Sun out there isn't a warm yellow disk anymore. It's a sharp, distant pinpoint brighter than any star but colder than any noon you've ever felt. This is the realm Triton circles in, a frozen, twilight world drifting through one of the darkest regions of the solar system. And yet, when scientists look at it carefully, what they find is anything but dead. In simple terms, Triton is the 7th largest moon in our solar system. It's slightly bigger than Pluto, slightly smaller than our own moon, about 1,680 miles across. From a distance it looks pale, almost ghostly. Parts of its surface shine in soft pinks and salmon tones, while other regions are tinted blue-white from frozen nitrogen reflecting the faint sunlight. It's a beautiful world, in the way that frozen things can be beautiful. Quiet, still, distant. The kind of place you'd expect to be locked in eternal silence. But the moment you start studying it closely, you notice something off, something wrong. Something that, once you see it, you can't unsee. Triton is going the wrong way. Every other large moon in our solar system orbits its planet in the same direction the planet itself spins. This isn't a coincidence. It's a leftover fingerprint from how moons are born. When a planet forms, it pulls together a swirling disk of gas and dust, and out of that disk, smaller bodies coalesce. Because the disk is rotating in one direction, every moon born inside it ends up rotating and orbiting in that same direction. It's like a record player. Every dust speck on the spinning vinyl moves the same way. You don't get one piece of dust suddenly running backward against the groove. The physics simply doesn't allow it. But Triton runs backward. It orbits Neptune in the opposite direction. Neptune spins. Imagine standing on a busy highway where every single car is driving north, and then suddenly, in the middle of the lanes, one car comes screaming southward at full speed. That's Triton. It's the only large moon in the entire solar system doing this. And once you understand that detail, the whole story of Triton starts to crack open, because if Triton orbits backward, then Triton couldn't have formed where we found it. The physics that creates a planet's family of moons simply does not produce backward orbits. So the only explanation left is the one that sounds, at first, like science fiction. Triton wasn't born around Neptune at all. It came from somewhere else. It was caught. This is where the story gets strange in the best possible way. When astronomers studied Triton's chemistry, its surface ices, its density, its overall composition, they found something almost shocking. Triton looks almost identical to Pluto. Same kinds of nitrogen ice. Same methane, same water ice, same carbon dioxide, same approximate density of about 2 grams per cubic centimeter. If you placed Triton next to Pluto in a lineup, you'd struggle to tell them apart in any meaningful chemical sense. They look like siblings. And that's because, in a very real way they are, Pluto lives in a region called the Kuiper Belt. A vast, distant ring of icy bodies orbiting the Sun far beyond Neptune. It's a kind of frozen graveyard left over from the birth of the solar system, full of dwarf planets and frozen worlds we've barely begun to explore. Almost everything out there shares the same chemistry, the same icy makeup, the same low density. And Triton fits that profile perfectly. So scientists came to a conclusion that, once you accept it, changes how you look at our entire solar system. Triton was originally a Kuiper Belt object. It used to orbit the Sun on its own, just like Pluto does today, until something pulled it in. The leading theory is called the binary capture model, and it's one of the most dramatic stories in planetary science. Imagine that long ago, billions of years ago, Triton was part of a pair. 2 icy bodies orbiting each other as they drifted slowly through the outer solar system, the way Pluto and its largest moon Charon orbit each other today. For untold ages, this binary pair circled the Sun in peace. And then one day, they drifted too close to Neptune. Neptune's gravity reached out, grabbed the pair and tore them apart. One member of the pair was flung away into deep space, lost forever. The other, Triton, was captured into orbit around Neptune. And because of the angle and direction of that capture, Triton ended up orbiting backward, against Neptune's spin. The retrograde orbit isn't a quirk, it's a scar, a permanent record of the violent moment Triton lost its partner and gained a new home. That single realization is the first reason why Triton matters so much to modern science. Because if Triton truly is a captured Kuiper Belt object, then studying Triton up close is essentially studying a Kuiper Belt world without ever having to send a spacecraft all the way out there. Pluto is so far away that the New Horizons mission took almost 10 years just to reach it. But Triton is right there, locked in orbit around Neptune, holding on to the same kind of ancient, primitive material that's been preserved in the deep freezer of the outer solar system since the dawn of the planets themselves. It's a shortcut, a captured fossil, a piece of the Kuiper Belt brought close enough for us to actually study if we ever decide to look. And the more closely scientists have looked, the stranger Triton has become. Take its temperature, for example. The surface of Triton sits at roughly -391 degrees Fahrenheit. That's -235 degrees Celsius. To put that into perspective, that's not just cold. That's the coldest surface temperature ever directly measured anywhere in the entire solar system. Colder than Pluto. Colder than the night side of any other moon we've ever pointed an instrument at. And here's the part that catches people off guard. Triton is closer to the Sun than Pluto is, so it should, by simple logic, be a little warmer than Pluto. But it isn't. The reason comes down to one of the most underrated properties in physics: reflectivity, or in scientific language, albedo. Triton's surface is so bright, so smooth, so coated in pristine nitrogen ice that it reflects roughly 70% of the already faint sunlight that lands on it. Imagine standing on a snowfield at dawn, where the surface is almost too bright to look at. Now multiply that effect across an entire moon. Most of the warmth Triton could absorb just bounces straight back into space. Pluto, by comparison, has a darker, dustier surface that holds onto a little more of the sun's energy. So Pluto, despite being farther away, ends up slightly warmer. Triton is the cooler twin, the frozen vault. And that extreme cold has a strange consequence: it preserves chemistry. Whatever was on Triton's surface billions of years ago, when the moon was first captured, is still largely there today, locked in ice. Triton is, in many ways, a time capsule of what the early outer solar system looked like. Even its atmosphere is a kind of fossil. Triton has one, though just barely. It's a thin, ghostly layer of nitrogen, with traces of methane and carbon monoxide. About 70,000 times thinner than the atmosphere we breathe here on Earth. If you stood on Triton, you wouldn't feel any wind. You wouldn't hear any sound. The pressure would be so low that water in your blood would boil away instantly. And yet, this whisper of an atmosphere is real. It has clouds. It has haze. It has a kind of seasonal cycle, where nitrogen frost sublimates from one hemisphere and freezes onto the other as Triton's long, slow seasons shift. Each season on Triton lasts about 40 Earth years. Imagine a winter that takes a generation to end. And then there's the color. Parts of Triton glow with a soft pink-red hue, almost like a frozen sunset trapped on the surface. That color isn't random. It's the result of something fascinating. When sunlight, even the weak, distant sunlight that reaches Neptune's neighborhood, hits methane in Triton's atmosphere, it slowly breaks the methane apart and rebuilds it into more complex molecules called tholins. These are the same kinds of organic compounds that scientists believe are tied, in some deep way, to the origins of biological chemistry. Tholins coat the surfaces of Pluto, Titan, and Triton in soft pinkish layers. They are, in a sense, the prebiotic chemistry of the outer solar system, the molecules that come just before the molecules of life. And they're all over Triton. Now stop and take stock for a moment. Already, just from the things we've talked about so far, Triton is unlike any other moon. It was born somewhere else, in the wild outer reaches of the solar system. It was violently captured by Neptune billions of years ago, leaving behind a backward orbit as the only clue. It is the coldest measured surface in the solar system. It preserves the same chemistry as Pluto, giving us a free, up-close window into the Kuiper belt. And it carries, on its surface, the kind of organic molecules that hint at the chemistry of life. Any one of those facts would make a moon scientifically important. Triton has all of them, and yet, somehow, this is still only the first half of the story, because everything we've talked about so far is about Triton's past, where it came from, how it got here, what it's made of. We haven't yet talked about what's happening on Triton right now, today, while you and I are alive. And that's where Triton stops being just a fascinating frozen world and starts becoming something much harder to ignore. Because in 1989, something happened that nobody was prepared for. NASA's Voyager 2 spacecraft, after 12 years of traveling through the solar system, visiting Jupiter, Saturn, and Uranus along the way, made one final stop before heading out into interstellar space forever. It flew past Neptune, and as it swung around the planet, it pointed its cameras at that strange, backward orbiting moon and took the first, and, as it turns out, the only, close-up photographs of Triton that any human being has ever seen. What Voyager found was not what anyone expected. The working assumption, before that flyby, was simple and reasonable. Triton was far from the Sun. It was impossibly cold. It had been orbiting Neptune for billions of years. So it should be dead, geologically dead, like our own moon, like most moons in the outer solar system. A frozen ball of ice with ancient craters and nothing else to say. A world whose story ended a long time ago. But when the images came back to Earth, the scientists at the Jet Propulsion Laboratory went quiet, because what they were looking at didn't make sense. Triton's surface was almost entirely free of impact craters. In planetary science, craters are like wrinkles on a face. They tell you age. A surface covered in craters hasn't been touched in billions of years. A surface with almost no craters has been resurfaced recently. Something erased them. Something refreshed the ground. Triton's face was young, impossibly young for a world so old. And that meant one thing. Something on Triton was still active. And then they saw the geysers, dark streaks, miles long, stretched across Triton's southern hemisphere. And at the origin of some of those streaks, Voyager's cameras caught something extraordinary. Columns of dark material being launched straight up through Triton's thin atmosphere, reaching heights of roughly 5 miles before being caught by high-altitude winds and dragged sideways into long, smeared trails. These weren't ancient markings. These were live eruptions, happening in real time. On a world where the surface temperature was nearly 400 degrees below 0 Fahrenheit, this was cryovolcanism. And it was the first time anyone had ever witnessed it happening on a world this cold, this far from the Sun. Let me explain what cryovolcanism actually means. Because the word sounds complicated, but the idea is surprisingly straightforward. On Earth, volcanoes erupt because molten rock deep underground gets pressurized until it forces its way through cracks in the surface. The mechanism on Triton is almost the same, except you replace molten rock with something far stranger. On Triton, the lava is liquid nitrogen, or sometimes a mixture of water and ammonia, substances that are normally frozen solid at Triton's surface temperatures but can become liquid or gaseous if enough pressure builds up beneath the ice. Here's how scientists believe it works. Triton's surface is covered in transparent nitrogen ice. When the Sun, even the faint, distant Sun that barely reaches Neptune's orbit, shines down on this ice, some of the light passes through it, the same way sunlight passes through a window. Beneath the surface, darker material absorbs that light and warms up slightly. And because the transparent ice acts like a greenhouse roof, trapping that tiny amount of heat underneath, the temperature beneath the surface slowly rises. Not by much, but on Triton, where everything is so close to the boiling point of nitrogen, even a tiny increase in temperature is enough to turn solid nitrogen into pressurized gas. That gas builds and builds beneath the ice cap, unable to escape until one day the pressure becomes too great. The ice cracks, and a geyser of nitrogen gas explodes upward, carrying dark dust and debris 5 miles into the sky. 5 miles. Think about that for a moment. Mount Everest is about 5.5 miles tall. These geysers on Triton are reaching heights that would nearly match the tallest mountain on Earth, on a world where the gravity is only a fraction of ours, and the atmosphere is almost non-existent. The material shoots up, hits the thin winds in Triton's upper atmosphere, and gets smeared sideways for dozens of miles, leaving dark streaks on the surface that Voyager was able to photograph from space. And the surface itself is equally bizarre. In parts of Triton's equatorial region, Voyager captured terrain that looks unlike anything else in the solar system. The ground is covered in a pattern of interconnected ridges and depressions that look, honestly, like the skin of a cantaloupe melon. Scientists literally named it cantaloupe terrain because there's no better description. It's a surface that appears to have been repeatedly churned, cracked, refrozen, and reshaped from below, over and over again, by internal forces that are still not fully understood. It's the kind of surface you only get on a world that is alive beneath the crust. A world where internal heat and pressure are still reshaping the landscape, even now, even in the coldest place we've ever measured. And this is where the implications start to become enormous. Because Triton is not the only moon in the outer solar system that shows signs of internal activity. Europa, orbiting Jupiter, has its cracked ice and almost certainly has a liquid ocean beneath it. Enceladus, orbiting Saturn, famously shoots plumes of water vapor into space from fractures near its south pole. These two moons have dominated the conversation about life beyond Earth for the past 20 years. But here's the thing that most people miss. Triton belongs in that same conversation. It belongs there for the exact same reasons. Because if Triton has internal heat and the geysers and young surface strongly suggest it does, then the question becomes where that heat is coming from. And the answer, just like with Europa and Enceladus, is tidal heating. Neptune's gravity doesn't just hold Triton in orbit, it squeezes it. Subtly, constantly, the way your hand squeezes a stress ball. As Triton orbits, Neptune's gravitational pull flexes the moon's interior, stretching it slightly in one direction and then another. That flexing generates friction. Friction generates heat, and over billions of years, that heat accumulates deep inside, warming the interior just enough to prevent everything from freezing solid all the way through. What this means, in practical terms, is that beneath Triton's frozen outer shell, beneath all that nitrogen ice and water ice and cantaloupe terrain, there is very likely a layer of liquid, an ocean. Not liquid water in the way we think of it on Earth, but a mixture of water and ammonia kept liquid by the heat of tidal flexing, sitting in darkness beneath miles of ice. An ocean that no human has ever seen. An ocean that might have existed for billions of years. An ocean that, if you think carefully about the conditions inside it, starts to sound disturbingly habitable. Because here's the thing that changed astrobiology over the past 30 years. We used to believe that life needed three things: liquid water, organic chemistry, and an energy source. And we used to believe that those three things could only come together in one kind of place. The narrow band around a star where sunlight keeps water liquid on a planet's surface. The so-called habitable zone. Earth lives in that zone. Mars sits at its edge. Everything else we assumed was too cold or too hot, but then we found Europa's ocean and Enceladus's plumes, and suddenly the rules changed. Because these moons get their heat not from the sun, but from gravitational tidal forces. They have liquid water, not because they're close to a star, but because their planets squeeze them. And that realization blew the old habitable zone wide open. Life doesn't need sunlight. Life needs energy and chemistry and water. And those can exist almost anywhere. Triton fits this model perfectly. It has the liquid water, almost certainly beneath its ice. It has the organic chemistry. Tholins are all over its surface and likely inside it too. It has the energy source, tidal heating from Neptune, ongoing for billions of years. These are the same three ingredients. The same argument that makes Europa and Enceladus serious targets in the search for extraterrestrial life applies to Triton with equal force. And in some ways, Triton is even more interesting than Europa or Enceladus, because Triton came from somewhere else. It wasn't born in the warm neighborhood of Jupiter or Saturn. It formed in the Kuiper Belt, the deep, cold, ancient outer reaches of the solar system. If Triton has a habitable ocean, then that means a Kuiper Belt object can develop the conditions for life. And there are thousands of Kuiper Belt objects out there, maybe tens of thousands. If life can take hold inside one of them, then the universe just got a lot more crowded. Triton, if it turns out to be habitable, wouldn't just be one interesting world. It would be proof that life has almost no limits on where it can begin. And yet, despite all of this, despite the geysers and the possible ocean and the organic chemistry and the rewriting of the habitable zone, humanity has only visited Triton once. One time in all of history. That Voyager 2 flyby in August of 1989 lasted just a few hours. The spacecraft passed at enormous speed, snapped a few hundred photographs of roughly 40% of Triton's surface, took some readings, and then kept going, heading out of the solar system forever. That's it. That's all we have. Every image of Triton's surface in every textbook, every scientific paper, every documentary, comes from that single pass. Data collected with technology designed in the 1970s. Cameras that, by today's standards, would seem almost primitive. We've never gone back. We've never dropped a lander onto Triton's cantilever terrain. We've never sampled its geysers. We've never sent a radar instrument to map the ocean we believe is hiding beneath the ice. Over 35 years have passed since Voyager 2's flyby, and in all that time, no spacecraft has returned to Neptune or its moons. Triton sits out there erupting, changing, possibly alive, and we're studying it with photographs taken when the Berlin Wall was still standing. There have been proposals. NASA considered a mission called Triton that would have flown by Triton in the early 2030s. It was designed to map the surface in far greater detail, search for evidence of the subsurface ocean, and study the geysers and atmosphere with modern instruments. It was ranked highly in NASA's Planetary Science Decadal Survey, which is essentially the master list of priorities that guides where America's space exploration budget goes. But Triton was not selected for final funding. It lost out to other missions. And as of now, there is no confirmed plan to send anything to Triton in the near future. That absence is, by itself, one of the strangest things about this story. We know Triton is important. The scientific community has said so repeatedly, and yet it remains unexplored. A world with active geology, a possible ocean, a plausible case for life, and a chemical makeup that could unlock secrets about the entire outer solar system. And no one is currently on their way there to look. It's the kind of gap that future generations of scientists will probably find bewildering. But there's one more thing about Triton that makes it unlike any other world in the solar system. Something that gives the entire story a kind of quiet weight that's hard to shake once you understand it. Triton is dying. Remember the retrograde orbit we talked about earlier. The fact that Triton goes backward, against Neptune's spin, that detail which already told us so much about Triton's origin, also determines its fate. Because when a moon orbits in the opposite direction its planet spins, the gravitational interaction between the two doesn't just hold the moon in place. It slowly bleeds energy from the moon's orbit. This is called tidal deceleration. Every orbit, Triton loses a tiny fraction of its orbital energy to gravitational friction with Neptune. And as it loses energy, it spirals inward, closer to Neptune, imperceptibly slowly but relentlessly. Over billions of years, that slow spiral adds up, eventually. Roughly 3.6 billion years from now, Triton will cross a boundary called the Roche limit. This is the distance at which the tidal forces from Neptune become stronger than the gravitational forces holding Triton together as a solid body. Once a moon crosses the Roche limit, it doesn't slam into the planet. It does something almost worse. It comes apart. The planet's gravity pulls harder on the near side of the moon than on the far side, and that difference in pull stretches the moon, cracks it, and ultimately tears it into countless pieces of ice and rock that spread out around the planet in a thin, flat disk. A ring. 3.6 billion years from now, Neptune will have a ring system, and it will be made from what used to be Triton, a moon that was born in the Kuiper Belt. That was violently captured. That spent billions of years erupting frozen nitrogen into its sky. that possibly harbored life in a hidden ocean beneath its ice. All of that history, all of that complexity, all of that potential, scattered into a band of glittering debris circling a dark blue planet in the outer solar system. And even the destruction of Triton, is scientifically valuable. Because it gives us a model. It shows us how ring systems can form. Saturn's rings, which are so iconic and so beautiful, may have formed through a similar process billions of years ago. Some ancient moon, spiraling inward, crossing the Roche limit, coming apart. Triton is giving us a preview of that process in slow motion. Its death will teach us how planetary systems evolve over cosmic timescales. So here, finally, is why Triton is one of the most important moons in space. Not for any single reason, but because of how many different questions it answers at the same time. Its origin tells us about the Kuiper belt and how planets capture wandering worlds. Its chemistry tells us about the building blocks of life in the outer solar system. Its active geology tells us that even the coldest, most distant worlds can be alive. Its possible ocean tells us that habitability might exist in places we never imagined. Its retrograde orbit tells us about the violence and chaos of the early solar system, and its slow death spiral tells us about the future, about how moons end and how ring systems are born. No other moon does all of that. Europa is fascinating, but it formed where we found it. Enceladus is extraordinary, but it's small and limited. Titan has weather and chemistry, but it belongs to Saturn's family. Triton stands alone as a world that was stolen from somewhere else, carried billions of miles, kept alive by tidal forces, and is now slowly being pulled toward a fate that will dismantle everything it has ever been. Right now, as you listen to this, Triton is out there, 3 billion miles away. Its geysers are firing, its surface is shifting. Its hidden ocean, if it exists, is sitting in the dark, doing whatever it does. And it's moving. Just a tiny fraction of an inch, closer to Neptune than it was yesterday. It has been doing this for billions of years before we arrived, and it will keep doing it for billions of years after we're gone. The entire drama of Triton, its capture, its eruptions, its possible life, its inevitable destruction, is unfolding right now, at this moment, whether anyone is watching or not. And that, more than anything else, is why it matters. Because the universe doesn't wait for us to notice it. It doesn't pause its most important stories until we send a spacecraft. Triton has been one of the most important moons in space since long before any human ever looked up at the sky. The only question is whether we'll finally go back and look before it's too late to see what's hiding beneath the ice.